Okay, welcome to the fourth installment of Exploring the Frontiers of Incompleteness. I just want to begin with a few words of background where what areas we've covered and what we're going to cover. So far we've seen Joel Hamkins, who argued for a radical form of pluralism, according to which, on one interpretation, the statements of classical logic are such that they have determinate truth values, but everything else is the world of pluralism. And then after that, Pfefferman argued for determinateness about statements concerning first-order arithmetic, but maintained that statements of second-order arithmetic were indeterminate. And then after that, we had Wooden arguing for determinateness at the level perhaps of CH, but being fairly open and letting the case rest on where future advances in the search for new axioms would lay. And so we've marched our way up the interpretability hierarchy from weak systems to stronger systems. And now what we're going to do is go back and march up the hierarchy, but pay a little more attention to the philosophical issues that arise along the way. In particular, what kind of evidence you can give for new axioms, and the associated question of realism at a given level of the hierarchy. So it's a pleasure to have Charles Parsons today, who's going to speak to us on evidence and the interpretability hierarchy, or the hierarchy of mathematical systems.
Well, I have to turn this on somehow. Not sure where this is. Does it say set? Is that the one that turns it on? That doesn't seem right. I haven't found the on-off switch. Sorry, I'm so unfamiliar with this thing.
It's a little worn down. There, I'll just put it back in my pocket.
Thank you. Is that okay? Well, as those who've attended courses of mine know, I'm rather fond of the history of the foundations of mathematics before the Second World War. And I've also been involved with Gödel, not personally, but with the documents. So this might strike some of you as reaching too far back into the past, but I think a lot of the epistemological issues that were posed at that time are worth bringing up, even if it turns out that they're not helpful for the problems that most interest Peter. Okay. It's a well-known fact of mathematical logic, by now developed in considerable detail, that formalized mathematical theories can be ordered by relative interpretability, and the strength of a theory is indicated by where it stands in this ordering, which is a partial ordering modulo the equivalence relation mutual interpretability. And of course, of the theories that have been studied, the ones that have a claim to be natural belong to a linearly ordered subset in this ordering. In a lecture of 1934, when the study of these matters was in its infancy, Paul Bernays gave a classic discussion of different foundational standpoints that ordered them roughly according to the degree of strength of what he called the Platonist assumptions that they embodied. This doesn't coincide anything like exactly with the hierarchy based on interpretability, as is shown by the fact, which was a pretty new result when Bernays mentioned it in his lecture, that classical first-order arithmetic, PA, is interpretable in intuitionistic, HA, and since HA is a subsystem of PA, it follows immediately that they're mutually interpretable. So I'm going to present this hierarchy rather briefly, but just a couple more preliminary remarks. About what Bernays means by Platonism, I'll just call your attention to the long quotation on page 1 of the handout, where I think the sort of business part is in the middle. We're talking about a certain totality of objects. It's objectively determined whether there is or is not an element of the totality that possesses this property. Similarly, it follows from this point of view that either all the elements of a set possess a given property, or there's at least one that doesn't. So that version of the law of the excluded middle is what's most essential to Platonism as Bernays understood it. His scheme was set forth somewhat more systematically by Hao Wang in a paper of 1958, although he used the word Platonism in a way that differs from Bernays' original, and I'm going to stick closer to Bernays. In recent years, questions about evidence in mathematics and many questions about realism center on higher set theory. It's an interesting fact that in the great foundational debates of the interwar period, higher set theory was hardly discussed. This is somewhat ironic in view of the fact that it was Cantor's development of set theory and the application of set theoretic methods in mathematics that touched off the foundational debates of the early 20th century. But especially when one takes up set theory, Bernays' classification does relate to the interpretability hierarchy, and I'll mention some relations as I go on. I will add to his own and Wang's version of this hierarchy some points that have come up really only in relatively recent years, at least in the post-war period. Well, Wang's paper was 1958, say the post-1960 period. Then in the later part, I'll discuss some rather general epistemological approaches to mathematics in the light of this hierarchy, and specifically in the light of problems of set theory. Well, the lowest point that Bernays and Wang consider is strict finitism, what Wang called anthropologism. Bernays didn't really register it as a foundational standpoint, but he did question, is it really intuitively evident that a number described by a stacked exponentiation can be represented by an Arabic numeral, and makes the remark that one could introduce the notion of what he calls a practicable procedure and implicitly restrict the import of recursive definitions to practicable operations. I would want to distinguish, though, between the kind of strict finitism that's identified with Edward Nelson, where one has a rather specific mathematical characterization, at least mathematical limitations, and therefore ignores the fact that very intuitively the idea of feasibility of computations is a vague one. And actually that was one of the sources of the discussion of vagueness in post-war analytic philosophy. In the paper Wang's Paradox by Michael Dummett from the 1970s. But Peter said a lot about strict finitism, and I'm going to just leave that matter there. Finitism is, of course, the number 2. Incidentally, the numbering on the paper as posted on the web was wrong. I skipped a number. Finitism is to be roughly the domain of mathematics intended by the Hilbert school as appropriate for proof theory. There have been differences of opinion about what that includes, but there's certainly agreement that on any reading it's naturally represented by a free variable formalism, and that the strength of this formalism would fall short of or barely reach that of Peano arithmetic. Nothing in this talk is going to turn on it, but I would be inclined to follow William Tate, our next speaker, who gives an analysis according to which the finitist functions are exactly the primitive recursive functions. Hilbert and Bernays aimed at intuitive evidence. Tate's analysis steers clear of that notion. I have, of course, done a lot with such ideas, successfully or not, and that will come up again. Bernays' next item is intuitionism, the famous tendency founded by the Dutch mathematician L.E.J. Brouwer. Seeing it from the point of view of finitism, what distinguishes it is that it allows logical combinations of quantified statements rather than a free variable formalism. So, for example, at the level of first order arithmetic, intuitionistic and classical have the same language. It's this liberality about expression combined with the insistence on constructivity at every step that leads to questioning and giving up, in effect, the law of the excluded middle. Brouwer's intuitionism allows richer second-order means of expression to accommodate analysis. Functions, in a way, are more fundamental than sets, at least in formal systems for intuitionistic analysis. For Brouwer, analysis is closely intertwined with his own theory of ordinals, which is in effect a theory of constructive ordinals that doesn't depend on recursion theory. Which he used with his famous Bar theorem to prove that every function everywhere defined on a closed interval is uniformly continuous. But the point that's relevant is that in terms of interpretability, all versions of intuitionistic analysis are a great deal weaker than classical second-order arithmetic, even with the comprehension principle restricted to be pi 1, 1. It is, however, stronger than predicative analysis, which I'll come to in a moment. Come to next, in fact. This, according to Bernays, is the weakest version of Platonism because the law of the excluded middle is allowed for quantification over natural numbers. But sets of numbers, and therefore real numbers, have to be definable in a way that avoids the circumstances that led some earlier writers, Weil most convincingly, to make claims that there was a vicious circle in analysis. Sets have to be defined in a way that involves quantification only over domains that have been, so to speak, settled at an earlier stage. So you get a ramified hierarchy. Well, as a positive construction, this idea was inaugurated by Weil, but was not pursued really until after the war, first by Lorentzen and Wang, and then by efforts aiming more to analyze what predicativity is than to advance predicativism as a point of view. And that led to the widely accepted analysis of predicative provability given by Solomon Pfefferman and Kurt Schutte. Pfefferman liberated it from ramified theories. And for example, it described a second-order theory that he argued exactly captured the totality of what is predicatively provable. These theories took the natural numbers with first full induction as given. One should distinguish between predicative provability and predicative reducibility. The system ATR0 of Harvey-Friedman, which is proof theoretically of the same strength as the theories of Pfefferman and Schutte, but it has theorems that by their lights are not predicatively provable. It is a conservative extension for some level of arithmetic sentences. I don't have in mind exactly what. Well, the next sort of very natural step would be to be Platonistic in Bernays' terms about arbitrary sets of natural numbers. That, of course, is what one does in full second-order arithmetic, which turns out to be quite a powerful theory. And in particular, it's quite beyond the reach of proof theoretic analysis as it now stands. But then the power set axiom, of course, gives rise to a kind of iteration of going from a domain to all subsets of the domain. And if one does that iteration rather freely, one gets the hierarchy of sets. So that is, so to speak, the highest stage in this Bernays-Wang scheme. There's a quotation from Bernays on page 3 of the handout. Well, some additions need to be made from a more contemporary point of view. Strict predicativity, I will just mention. It's based on the idea that there's something impredicative about the concept of natural number as usually deployed. What's more significant is what I call extended intuitionism. That is, Brouwer's ordinals are a constructive second number class, but he didn't provide for higher number classes, which proof theorists found they needed in order to get anywhere much beyond predicativity in dealing with second-order arithmetic. So they began to work with higher constructive number classes. And Per Martin Luth, a little bit later, developed his intuitionistic theory of types, which provides for that and quite a bit more. In its full development, it's quite a bit more powerful than anything developed to formalize Brouwer's intuitionism. Well, where does intuitionism extended in that way stand in this interpretability hierarchy? Well, I'm not sure we know exactly, but Martin Löf argued in a paper published a few years ago that no constructive principles are in sight that would extend his theory so that it would even be able to interpret second-order arithmetic with comprehension restricted to pi12 formulae, where there was a proof-theoretic result in the 90s by Michael Ratjen, and Martin Löf viewed Ratjen's method as more akin to set theory than really constructive. Ratjen himself proposed a bound for what could be done with Martin Löf's type theory, but it's not clear to me how high that bound is. But in relation to, say, ZF, I'm sure it is very low. Writers on foundations often make a distinction between ordinary or classical mathematics and set theory or set-theoretic mathematics. I don't think it's been made out that this is a principled distinction, but I think some people who've made that distinction would place the boundary somewhere where Martin Löf thinks the limit of his extended intuitionistic theory. Well, the final extension of this scheme would be to make some distinctions within set theory. And there, of course, the strength of set theories beginning with ZF is typically calibrated by large cardinal axioms for reasons which, if you've been listening to Peter, you're familiar with. Two distinctions, though, suggest themselves. They're 6.5.1 and 6.5.2 on page 4 of the handout. First, the internally set-theoretic one between such axioms as are and such as are not compatible with V equals L, usually expressed as the distinction between small and large cardinals. Secondly, the more epistemological distinction between axioms that, as Gödel put it, are implied by the concept of set, often said to have intrinsic justifications, and those that don't have that, and the ones that for which such justifications haven't been suggested, I think are ones that we don't have a good idea as to how to argue that they are, in Gödel's terms, implied by the concept of set. Peter Koellner's paper on reflection principles would imply that the axioms that are implied by the concept of set are insufficient to yield the existence of a certain small large cardinal. So this second distinction draws a line at a lower point than the first one. Well, now I'm going to turn to some epistemological ideas. And relate them in some way to this hierarchy. It is an uncomfortable fact that justifying a theory, one would expect it to show that the theory is consistent, and then by the second incompleteness theorem, there has to be some respect at least in which the justifying theory is stronger than the theory that is justified. That's a kind of limit on what we can do in justifying theories. I don't think it has to be stronger in all respects. So, for example, Genson's original consistency proof for PA and other such proofs can be carried out by adding to primitive recursive arithmetic, according to Tate, finitist, a single instance of induction on a primitive recursive ordering whose order type is epsilon 0. So the kind of stacking of quantifiers that proofs in PA and also in HA allow would not be formulable in this theory that's sufficient for a Gentzen type argument. But anyway, the mathematical constraint would suggest that for higher domains of mathematics, we have to deploy less elementary epistemological ideas. I'm going to mention two somewhat traditional suggestions about the epistemological basis of mathematics. Intuition more or less on the Kantian model, and some form or other of empiricism. Well, one can't apply Kant's ideas too directly. First of all, there are disputes about its interpretation. And secondly, Kant was, after all, dealing with the mathematical situation of the late 18th century. But through the 19th century, when writers on mathematics talked about intuition, they had in mind something that shares with Kant some sort or other, with Kant's intuition that is, some sort or other of reference to space and time. The insistence of writers like Frege, who was not alone in this, that arithmetic and analysis should not depend on intuition, is against the background of that understanding of what the relevant concept of intuition is. The case of Frege is maybe particularly clear because he maintained a version of the traditional view of geometry as resting for its evidence on spatial intuition. Well, Brouwer's and Hilbert's conceptions of intuition are also descended from Kant's and certainly have this spatio-temporal character, although Brouwer insists that the intuition underlying mathematics is purely temporal. It doesn't follow that either of them has a philosophy that is, in any broader sense, Kantian. Well, following the model of Hilbert, Brouwer, and Bernays, I've set forth in several writings ideas of intuition and intuitive knowledge that are applicable to arithmetic. The conception of intuitive knowledge is not as clear as it should be, but it seems to me to track the idea that the Hilbert school starts with reasonably well. It should follow that what's intuitively known in arithmetic should coincide with finitist arithmetic, and that was the opinion of Hilbert, Bernays, and also Gödel. So it would follow that the functions that can be seen intuitively to be total should be closed under primitive recursion. There are explicit arguments to that effect in two writings of Bernays, one specifically about exponentiation and one more general. I wasn't able to convince myself that these arguments were valid and concluded that Hilbert and Bernays didn't have a non-question begging argument for the conclusion that primitive recursive functions are finitistically admissible, and that the obstacle is exponentiation would suggest that on the conception of intuitive knowledge I was after, intuitive arithmetic should coincide at least approximately with Nelson's strict finitism. There's the question of quantifiers in Nelson's scheme, but I'll put that aside. I won't pursue this further because even if my claim is quite wrong, no one would argue that the type of intuitive evidence appealed to by Hilbert and Bernays would extend much further than what they claim. it couldn't be the epistemological basis for all of mathematics, except on a very restrictive conception, probably more restrictive, for example, than Brouwer's version of intuitionism. Well, let's turn to empiricism. Some form of empiricism, taking its principal inspiration from W.V. Quine, we, by the way, now got to page 5 of my overlong handout, has almost dominated the conversation in American philosophy of mathematics. The Vienna Circle's attempt to reconcile empiricism with the apparently a priori character of mathematics, even in the subtle form given to it by Carnap, has in more recent years not found wide acceptance in spite of the more sympathetic view that has been taken of Carnap's philosophy more generally. At any rate, I don't personally feel enough at home with the issues it poses to address it in this context. Much more influential has been the holistic form of empiricism championed by Quine. That's the point of view underlying the much-discussed indispensability argument. Accepted mathematics must be true, and the objects it refers to must exist, because mathematics is indispensable for the natural sciences. Before one enters into any details, the question immediately arises how much mathematics is indispensable for science. In particular, Solomon Pfefferman has argued that the mathematics that's applicable in science can be formulated in a basically predicative theory. It has also been argued that the indispensability argument is at odds with the practice of mathematicians who don't seek a minimal theory as the indispensability argument suggests that they should. We don't need to pursue these issues because it's hard to see how, at least at the present stage in the development of science, considerations of indispensability could lend justification to much of higher set theory. Considerations of smoothness of theory might well lead to a significantly stronger theory than what Pfefferman describes, but why should it lead to an inexhaustible ascent into higher and higher reaches of the cumulative hierarchy? Gödel speculated years ago that strong axioms of infinity might find application in science, but the actual development has not led in this direction. It would seem more natural from this point of view to close off the ascent at some point high enough for any scientific needs, but still so as to yield a reasonably simple theory. Quine indeed suggests this at one point advocating V equals L as an axiom. Well, the conclusion I draw from these rather hastily sketched considerations is that some level of rationalism is unavoidable in the epistemology of mathematics, unless one jettisons higher set theory, which I'm not prepared to do. And then there's a gain in intuitive naturalness in admitting it short of higher set theory, even at the beginning of arithmetic. One naturally turns to logic because many thinkers find, say, first-order logic to be self-evident. Quine regards at least the sort of axioms and rules of inference as first-order logic as obvious. He doesn't give philosophical weight to that, or very much philosophical weight to it. But he also doesn't consider a caution that was voiced many years ago by Brouwer, Weil, and Hilbert, which I would put as follows. Logic is entangled with mathematics. Although first-order logic presupposes no ontology beyond the trivial presupposition of the non-emptiness of the domain, to see that an inference is not valid or that a sentence is not logically true, one may need to construct countermodels where the domain may be arbitrarily large up to countable infinity. Even if one argues from non-derivability and appeals to the completeness theorem. That won't change. What Brouwer, Weil, and Hilbert argued is that the applicability of classical logical inference in reasoning about the infinite is an assumption that can be contested. Hilbert maybe is the one who pressed the point furthest in his motivating considerations about his version of finitism. It's natural to think that if anything assumed in mathematics is rationally evident, basic logic must be. I think the critical case I've alluded to makes it reasonable not to regard it as self-evident, and the entanglement of logic and mathematics implies that it can depend on the mathematical context. Still, one can hardly doubt that mathematics based on classical logic has stood the test of time. Constructive mathematics has its own interest, but in no case not based on some first philosophy has been made for the claim that it deserves to displace classical mathematics. There have been suggestions that constructive logic should be used in statements about absolutely all sets, but I don't think that adds up to a case that one can't safely use classical logic in the reasoning that set theorists engage in about the universe. Well, this should leave the reader confused, what I've said about logic. In what sense are the classical logical inferences in a mathematical context rationally evident? There's an intrinsic difficulty, not with the evidence of logic itself, but with disentangling two different grounds on which it could be said to be evident. The idea of self-evidence is usually taken to imply that if a proposition is self-evident, then it's evident by itself. I tried to capture this by proposing that a statement is self-evident if it's evident to anyone who exercises a sufficiently clear understanding of what it means. Almost any claim of self-evidence can be disputed, but there are cases from logic that are as good as any. If A then and B then A, or if or the inference from if A then B and if A then not B to not A. It will be claimed that instances of A or not A are self-evident if one understands them in their classical meaning. But that's a way in which claims of self-evidence can be contested, because an intuitionist will claim that in cases involving the infinite, the classical meaning is itself based on illusion. But there are weaker degrees of rational evidence than self-evidence. Maybe the weakest of all is what I've called intrinsic plausibility. A statement is treated as intrinsically plausible if one's prepared to give it at least a certain amount of credence when it's not the conclusion of an argument or prompted by an external event, such as perception. Well, that implies that intrinsic plausibility admits of degrees. But it's reasonable to think that in some cases, including mathematics, intrinsic plausibility is objective, not down to some minutiae about degrees, but with some flexibility about degrees. Most of us would regard the axioms of classical mathematical systems as intrinsically plausible to quite a high degree. The matter's a little more contested when it comes, let's say, to ZFC. How much of that Pfefferman would grant, for example, I'm not sure. And of course, Brouwer would not grant it at all. would not have granted it. But there's still a difficulty about these notions that's suggested by holistic views of evidence and meaning. It's posed most sharply if we consider elementary logic and arithmetic. These branches of knowledge have had elaborate deductive development and application for centuries. We find the axioms and elementary inferences evident. But why should we be sure that this evidence is intrinsic? Aren't we appealing to this long history of development and application? Shouldn't we rather speak, as Paul Bernays does in some of his later writings, of acquired evidence? I think there are general, one might say, phenomenological grounds for thinking that the most elementary evidences in arithmetic are intrinsic, or at least resting on significant intrinsic plausibility. For example, such steps as passing from a natural number to the next are clear to school children who have little idea of the extent to which arithmetic has been developed in the course of history. Another is the conviction that arithmetical truths are necessary, so contingencies of the natural world or of history won't upset them. In the case of mathematical induction, when mathematicians first began to reason in a way that we would render as applications of induction, there simply wasn't a background of deductive development from a principle of induction or a least number principle. It's hard to see on what grounds other than intrinsic plausibility mathematicians of that time could have accepted inferences by induction. I think maybe the same could be said about in the prehistory of the axiom of choice and some of Zermelo's examples of implicit applications of the axiom of choice before he formulated it. Of course, the development and application of a mathematical theory can cause its assumptions to have a higher degree of evidence, maybe a much higher degree. I've let a lot of time by just getting to set theory. There, matters are confused by the fact that a wide variety of considerations of very different kinds have been offered to justify or motivate axioms of set theory. That raises the question whether any axiom of set theory is intrinsically plausible for more than a small degree, or at least treated as such, since arguments are offered for all of them, or nearly all of them, maybe not extensionality, pairing. But these arguments are rarely intended to be convertible into mathematical proofs. They're offered usually in the context of the iterative conception of set, or at least a whole class of such arguments are offered in that context, and are generally intended to show that the axioms fit into the general picture of that conception. In other words, to persuade us that given that conception, we should accept the axioms as implicit in it, or at least in harmony with it. That brings us to the notion of being implied by the concept of set, but I'll put that off for a while. Basing themselves on remarks of Gödel, writers on set theory have distinguished between intrinsic and extrinsic justifications. A common view is that the axioms of ZF and large cardinals, axioms at least up to a point, have intrinsic justification, while we don't have an idea for such a justification of large cardinal axioms. The intrinsically justified ones are the ones that Gödel called implied by the concept of set. And that seems to be a form of analyticity closely related to truth by virtue of meaning. I'm going to skip entirely the question of what analyticity meant to anyone other than Gödel. An interesting feature of Gödel's reflections on mathematics is that in his earlier philosophical writings, he's highly critical of the positivist point of view, but nonetheless maintains that there's an important sense in which mathematical propositions are analytic. The relevant sense is the second of the two that he discusses near the end of the paper, Russell's Mathematical Logic. That's the first of the quotations from Gödel on page 5 of the handout. The two further quotations are different, somewhat briefer formulations, but avoid this kind of doubling that's suggested by talking about the meaning of the concepts in a statement. Already in the Russell paper, Gödel indicates that it's his conceptual realism that makes it possible for him to maintain that the axioms of mathematics are analytic in this sense, while mathematics consists of statements with what he calls a real content, contrary to the view the Vienna Circle aimed at. If a statement is true by virtue of certain concepts, then he says the existence of these concepts will itself be a substantial assumption. So he says in his Gibbs lecture of 1951 that this meaning consists of certain concepts which form an objective reality of their own, which we cannot create or change, but only perceive and describe. That's the second of the quotations under number 2 on page 6. A mathematical proposition still may have a very sound objective content insofar as it says something about the relations of concepts. The way this is manifested is that axioms of mathematics are not tautologies or analytic in a narrower sense he proposed in the Russell paper, but still follow from the meaning of the primitive terms. He also suggests a relation with his ideas on mathematical intuition, which he develops in later writings, beginning with the unfinished Is Mathematics Syntax of Language. It's rather clear that essential to mathematical intuition, as he conceives it, is perception of concepts. And he regards it as a presupposition of an instance of analytic truth that the concepts involved exist, as he puts it. Gödel treats predicates as having concepts as at least something like reference, so that some level of perception of concepts is involved in understanding a language. But he makes clear that one can perceive concepts more or less clearly, and some examples he cites, such as Turing's analysis of computability, suggest that mathematical analysis and proof can lead to clearer perception of a concept. If the axioms of set theory force themselves on us as being true, as Gödel claimed in the 1964 version of the Cantor's continuum problem paper, then this would be described as our perceiving the concept of set with enough clarity. It's that he has in mind in speaking of something like a perception of the objects of set theory. And he describes this perception as mathematical intuition. That suggests a conjecture which I seem to have neglected to put onto the handout, which is the following. According to Gödel, a mathematical proposition is derivable from axioms knowable by intuition if and only if it's analytic, in the stronger sense from the Russell paper. This conjecture suggests a number of questions about Gödel. One consideration that speaks against it is that analyticity isn't mentioned as such in the 1964 version of the continuum paper, which is the publication of his where intuition is mentioned most prominently. Analyticity is also not mentioned in Wong's record of his conversations with Gödel. But there are indications that analyticity is still present in 1964 when he talks about axioms for inaccessible and Malo cardinals only unfold the content of the concept of set explained above, which is, I think, essentially the iterative conception of set. It's really a conception of the universe of sets and its structure rather than a conception of what an individual set might be. And he also talks about large cardinals in a footnote and says that it has not yet been made clear that these are implied by the general concept of set. Suggesting that he thinks they must be implied by it. But he doesn't seem later to feel closer to making this clear or to be especially optimistic about the prospect that others would accomplish this. And that may be a reason why analyticity doesn't appear in the record of the conversations with Wong. Of course, he pursues the idea of extrinsic justification of axioms, but that even goes back to the Russell paper. Well, the notion of intrinsic justification has been deployed by some writers after Gödel. I think it raises two questions. First, let's suppose that we have a convincing argument that a certain axiom is implied by the concept of set. Does that imply that it's true? Well, Gödel regards it as a substantial issue whether the concept exists. I don't think this means merely that the terms we take to express the concept are not nonsense, that we're able to understand and talk about sets in the language of set theory and make sense of the idea of the cumulative hierarchy. After all, we could do the same with Frege's extensions characterized by axiom 5. I think Gödel intended by the existence of a concept there being something that answers to it. In the language of Tony Martin, that the concept is instantiated. Martin himself is not without doubt as to whether the concept of set in the relevant sense is instantiated, because he takes seriously the categoricity argument going back to Zermelo, and therefore is inclined to hold that there is at most one concept of set which would, so to speak, fix the structure, but in that structure the continuum hypothesis must be true or false, but about that Martin is not convinced one way or the other, so he considers it a real possibility that the concept is not instantiated. So an issue that arises is, well, whatever is implied by the concept, is it instantiated? Now, Martin thinks of it as involving the two maximality power properties. You really have the full power set, and you really have an absolute infinity of levels. A weaker condition would be consistency or coherence of our theories. I'd understand coherence as something more than consistency, but exactly what that more is hasn't been made clear either by me or by others. structuralists, including myself, have suggested that coherence of the theory of a structure should be sufficient for being in a position to make true statements about objects in the structure. But now, what is the more than consistency that's demanded? Well, I don't have a very clear idea, but I think it should imply the consistency of extensions of the theory that are motivated in a natural way. But, of course, that is not all that clear. And in particular, it's not clear to what extent the large cardinal axioms that have been much discussed satisfy that condition. Well, if we're talking about coherence of a theory, and we could start with a theory with lots of large cardinals. But then we know there are going to be more, including some that have not been thought of. Consistency is a syntactical notion, and in their deductive development, second-order theories don't differ essentially from first-order theories. So if the suggestion is on anything like the right track, the coherence of set theory doesn't imply that the concept of set as Martin understands it is instantiated. Furthermore, it's not evident a priori that there couldn't be different coherent set theories, possibly offering different verdicts concerning CH. And on the structuralist view, we would be entitled to assert existence of the sets that such a theory gives rise to. So in the case of different coherences, we'd have set sub 1 and set sub 2. I'm not saying that that is going to happen in the development of set theory. I think maybe the evidence is more, so far, is more against it than for it. Well, I'm sorry, I'm sort of losing my thread here, even though I have a manuscript. Well, I've emphasized the problem that various conclusions might be said to be implied by a concept such as that of the universe of sets, while it seems that for us to accept these conclusions as true, something more is required, either instantiation, as Martin understands it, or coherence of the resulting theory. That might suggest that on this conception of intrinsic justification, it's rather badly off. I would suggest that things are not as bad as they seem, because in practice, the working out of such justifications clarifies the concepts in such a way as to make at least coherence more likely. Well, what's the relevance of this to the ideas about rational evidence? In particular, if we see that something's implied by the concept, should it be rationally evident, maybe even intrinsically so? That doesn't seem to me to be obvious, and Gödel, by admitting that intuition is fallible, since our perception of the concepts involved might be more or less clear, allows for that. In a particular case, there might be a lot of working out of consequences and connections made with reasoning from around before this particular theory was formulated. The idea of power set is built into the iterative conception, so the doubts one might have about that axiom get shifted onto the issue of instantiation. And I'm not sure that replacement can be convincingly argued to be implied by the concept, but again, one could build that into the concept too. Well, I've gone on for a long time, but I want to make just one comment about extrinsic justification, about the case of the most impressive case of extrinsic justification that I know about, which Peter talked about at some length last week, based on the connections between large cardinals, particularly wooden cardinals, determinacy, projective determinacy, and ADL of R, and the extension of classical descriptive set theory that the application of determinacy led to. In the discussion after his talk in this series, Solomon Pfefferman offered an objection that I think is worth discussing. No doubt alluding to Gödel's remark that a mathematical theory might be confirmed as well as a well-established physical theory, Pfefferman claimed that in this situation there is no analog of observation. One just had a lot of connections among statements at a rather high theoretical level. Well, the set theorist might reply that the classical results of descriptive set theory could be regarded as analogs of observation because they can be proved in ZFC, and so are results that mathematicians at large accept and have accepted for some time. But suppose we don't accept that reply. Epistemologists have often argued that claims might be justified on the basis of coherence, where the sense of that word is not quite what it was in the previous section. It means that a body of knowledge hangs together, not just internally, but also in its relation to other knowledge and possibly plausible conjectures. So a pure holism about the justification of theories would be an example of a claim of justification by coherence. And I think such coherence is exhibited by the connections that were worked out mostly in the 70s and 80s and laid out by Peter last week, is a highly plausible claim about the status of the classical results. I think they may be better viewed on the analogy of the so-called considered judgments that arise in John Rawls's conception of justifying moral and political theories by a process that aims to arrive at reflective equilibrium. I think Peter meant to exhibit the set theoretic picture as having arrived at such reflective equilibrium. It doesn't fully satisfy the requirements of wide reflective equilibrium because there are outliers with philosophical theories that reject the whole business, but that's maybe a lot to ask. Well, does CH have a truth value? I'll just say I don't think that there's an a priori argument around that either to the effect that it does or that it doesn't. Just one comment about Hampkins. I think his argument is not what I had in mind by an a priori argument, because it's based on appealing to the general experience of conducting a rather vast variety of models of set theory, and on the more specific fact that one can flip the continuum hypothesis by forcing. Start with a model that satisfies it, create a forcing extension that doesn't satisfy it, and vice versa. The set theorists no doubt have answers to that argument, but it's not the kind of a priori argument that that I want to say is not available. And in general, what will convince one that there is a definite truth value is at least highly plausible and preferably fully convincing argument that tells us what the truth value is. Well, I'll stop there. And that is obviously not something that mere philosophers are going to get us much of anywhere. Thank you.
I have a question. Connected, the question's about the relationship between, it's a very big question, I guess, reason and realism. So at the end of the talk and the end of the paper, you say that CH can't be settled a priori by philosophy, and a convincing argument that it has a determinate, the statement that CH has a determinate truth value can't be settled a priori or by philosophy, and a convincing argument that it does have a determinate truth value will come through actually giving you what the truth value is. So that makes it look like the brand of realism that you have is coming after your views about reason. So in other words, it makes it look like by the way you understand those notions, you could never be in a situation where you thought that a certain statement had a determinate truth value, but also thought that, but where it was also the case that we didn't have reasons for thinking it was true, and we didn't have reasons for thinking that it was false. Is that correct?
I think that was meant to be a statement of the sort of situation where we know that there's a lot of conceptual difficulty there. We are not persuaded by any axiom that settles it, that can settle it. That is, we know that they do not settle it. That, I think, as I recall, you yourself said this in discussing Pfefferman's views. Why is CH different from the Millennium problems? Because the Millennium problems don't have that character. If they're solved, people expect them to be solved by in a way that so that the solution could be axiomatized using pretty standard mathematical axioms. Now, when the Fermat's last theorem proof first became known, there was the idea about that maybe strongly inaccessible cardinals were needed. I think it was fairly quickly made out that that isn't so. But I think from a set theorist point of view, strongly inaccessible cardinals are part of the standard mathematical repertoire anyway. I would think it wouldn't have been a big deal if it had turned out that they were needed.
Okay, so let me modify the question then. So it's not enough to just not have reasons one way or the other, clearly, to conclude that it doesn't have a determinate truth value. But if you had reason to believe that you could never give reasons for it, you could never give reasons against it, then you would think that that would establish that it has doesn't have a determinate truth value.
Yeah, well, how could you establish that? You take this sort of mythical suggestion that you might have two different set theories that were coherent. It would always be open, I think, to question whether one or the other really is coherent. Now, I'm afraid done too little to. I've done too little to make this notion of coherence clear. Well, something that came up in one of these talks, namely Freiling's dart-throwing axiom, which turned out to be exactly equivalent to not CH. Well, we don't. If we knew that that ZF plus Freiling's axiom was not coherent, then we'd know that CH is true. So we don't know that. But the various considerations that people have offered against his argument, I think, do show that he didn't make out that it is coherent, although it's consistent if ZF is consistent. Tim.
Charles, I wonder if you could say a little more about the idea of how to understand the question of whether the concept of set is instantiated or whether it exists. When one first hears that as a question, it sounds as if the answer is something that couldn't be discovered or settled by, as it were, coming to perceive the concept more clearly, to use the language you used, or working out more fully what follows from the concept itself on the best understanding. But at least in the negative, that wouldn't seem to be true. If I try to think about how I might arrive at the conclusion that the concept of set isn't instantiated, one way might be by coming to the conclusion that a kind of pluralism about sets is true, that there's set 1 and set 2, as you said. So our idea that there was such a thing as the concept of set turns out to have been a mistake. And we discover that by working out more clearly kind of what is or isn't, and it turns out to be too weak there. And so, as it were, falls apart. So that if that were an example, then that would be a way in which, at least in the negative, you could settle the question of whether the concept of set, as we originally interpreted it, was, or imagined it, was instantiated by simply further, more careful examination of that concept itself. But then the question is, suppose that doesn't happen. Suppose it becomes more and more and more coherent, those are things that we discover by more and more investigation, as it were, internal to our understanding of it. Is there still a further question about whether it exists, and how do you understand that question?
Yeah, okay, as things, you're imagining a scenario where as things develop, the picture, when difficult problems are resolved, never gives any decisive support to what Peter calls pluralism. And presumably also one never comes up with an inconsistency in set theory, no matter how many large cardinals one cooks up. At least one has an ascending sequence of large cardinals that doesn't give rise to. I think this idea of the concept of set being instantiated or not, of course it's more Martin's idea than mine, but something like that is probably the best evidence we could have that it is instantiated. I would think it wouldn't settle the matter once and for all, because who knows what the next generation of set theorists even higher up in the stratosphere might cook up. But it would, I think, tend to make it more, to make pluralism more implausible.
Is pluralism the only kind of, something like that, or an inconsistency, the only kind of thing you're imagining would settle in the negative, instantiate, whether it's instantiated, or is there some possibility, even though none of those things arise nonetheless, there's a further question about instantiation? That was what I was wondering. I was assuming, as I would think of it, not, but I was wondering whether, whether Martin understood it in a way such that was a possibility.
Yeah, I can't speak for Martin, but I think the main argument he gives is a kind of antinomy that would arise for in the case where you have some sort of convincing case that the continuum hypothesis doesn't have a determinate truth value, because set theory is categorical, and that determines the truth value of CH, but CH doesn't have a determinate truth value. Okay, how else might one come to this conclusion? I suppose short of inconsistency, things might turn up that just seem to be anomalies that one couldn't make sense of in terms of one's understanding of the concepts with which one started. But those anomalies might turn out to be resolvable. So I don't think that would be decisive.
Can I just talk loud? Yeah. This may just be a very simple-minded version of Tim's, or variation on Tim's question. I mean, as philosophers think of Platonism in terms of the existence of abstract objects and the need for abstract objects to exist to do mathematics, to do physics, and so forth, and to try to construct nominalist alternatives to Platonism in that sense. I mean, that at least seems to be a clear distinction that one might be interested in. Do we need abstract entities in order to do physics, to describe the world, or can we get away with tangible, or at least the entities described in physics? As you use the term, and as those you were speaking about use the term, it seems that they're all Platonists. Platonism, without using that term, Platonism refers to the existence of abstract entities of a particular sort, higher level, more complex structure, whatever. Is there anything comparable to the sort of clear and metaphysically clear distinction between abstract entities and tangible entities that philosophers can understand? It seems to be an important metaphysical distinction. And the distinction between Platonism and non-Platonism once we're in the realm of abstract mathematical entities?
Yeah, well, Bernays, I think, had a quite clear criterion of Platonism, which was a precursor, I think, of the ideas about realism that you find in the writings of Michael Dummett, starting when? Around 1960. And that's quite different from the idea that I think goes back to Goodman and Quan's paper on nominalism of 1947, that you're a Platonist if you admit any abstract entities at all. It's surprising how much you can do in mathematics on a more or less nominalist basis. There's a standard source on that subject, the book A Subject with No Object by Burgess and Rosen. But there's still a question, which at least for both of them I think is a very live question. Why should one want to do that? And I confess I have never been that much moved by nominalism as a point of view. You have to translate mathematics into some different language. And one version of nominalism, going back to Hartree Field in 1980, treats as nominalistically acceptable objects that are intuitively mathematical objects, namely points and regions of space-time. And that strikes me as a kind of cheating. Maybe the term Platonism is not all that helpful. I think Bernays used it in a very illuminating way in this paper, but that paper was written in the middle 1930s, and a lot of water has gone over the dam since then. I studied Bernays's post-war writings with some thoroughness, and have published something about them. And one thing I noticed is that he largely avoids the term Platonism in those later writings. I generally prefer the term realism, although realism is even more Protean than Platonism as a term. But it does have the advantage of not being less likely to raise red flags for people. Interestingly, by the way, one more comment. Gödel, in one of those letters to Wang of the late 60s that were first published in Wang's book, From Mathematics to Philosophy, uses the term objectivism. And that turns up in other documents not published even at that time, but do a little advertising. One of them is appearing within weeks in a book called How Wang, Logician and Philosopher, edited by me and by Monty Link. The title we gave to it is Sets and Concepts on the Basis of Discussions with Gödel. It's written by Wang, not by Gödel, but the terminology certainly comes from Gödel. Okay.